conference. We have a long session today, 7 talks. So get started on time, I guess. I have a quick announcement. Some of you may be interested in knowing that Jordan Ellenberg will be having a book launch this evening at 8 p.m. at Casa do Saber. So if people are curious, would be, some of you may be interested in going. So get started with our first speaker this morning, John Keating from the University of Bristol, will speak on arithmetic statistics over function fields.
Okay, well, thank you. Could I have my slides back? I don't know quite how to recover them. Where's the man? Ah, there. Well, thank you, and thank you to the organisers and all involved in putting this meeting together, which I think has been wonderfully interesting so far. What I'm going to speak about indeed concerns arithmetic statistics, statistical properties of arithmetic functions, and I'm going to be considering in particular the case where these are defined over function fields, where it seems one can prove things using techniques coming from random matrix theory, that is, from physics. So to motivate this, I'm going to talk about one particular arithmetic statistic in some detail to give you a flavor of the kind of context and motivation, and then I'm going to go through some other cases that have been of interest more recently to us. So the case I want to go through by way of an example concerns the distribution of the primes, and as is well known to everybody in this audience, one can count the primes, and one has an asymptotic for that counting function if one counts the primes over a very long range. So if you count the primes all the way up to x, then as x tends to infinity, one has this asymptotic for the counting function, which is just the prime number theorem. And the motivation for developing this asymptotic, the motivation for proving this theorem, of course, goes back to Gauss. And this is extract from a famous letter that Gauss wrote to Encke, where he recalls that in about 1792 or 1793, that's when he was about 15 or 16 years old, his pastime was to count the primes in various intervals, and he was very specific about what he did in these numerical experiments. He counted the primes in several chiliads. A chiliad is 1,000 consecutive integers. So he split the numbers up into chiliads, and in each chiliad he recorded how many primes there were, and then he says that this number fluctuated, but on average it depended inversely. It was inversely proportional to the logarithm, and that's what we now recognize as what was later proved as the prime number theorem. And for those who haven't seen it, I suspect many of you have, this is the data recorded in Gauss's hand. I think I got this from Yuri Schinkel's website, so thank you very much. So this is from that letter. So Gauss records that up to 500,000, that is in the first 500 chiliads. So this is getting the data for each chiliad and amalgamating it into groups. In the first 500 chiliads, about 41,556 primes, and the integral is just a little bigger than that, and the difference is very small. And in the first 1,000 chiliads, 78,501. That's a slight miscount, actually, but not by very much. Good enough for government work, I think, is the term. This is about the right number, and this is the integral, and again, the difference is small. And Gauss gave data up to 3 million, that is the first 3,000 chiliads, and again, the prime count that he set out is very close to the value of the integral. So we would say that the error term in the prime number theorem is experimentally, and this is the experimental data, very small. Now, of course, the prime number theorem was proved using analytic properties of the Riemann zeta function. This was Riemann's great insight. So the zeta function is defined here. It's a sum over a Dirichlet series, or it's an Euler product involving the primes. And the prime number theorem comes from the fact that this function has a pole at s equals 1, and that it then has no zeros to the right of that pole or on the line real part of s equals 1, and the fact that the zeros that do exist to the left of that line are not too dense. So that's how one proves the prime number theorem, and this was Riemann's tremendous insight, later systematized by others, Hadamard and Poisson. And of course, the Riemann hypothesis asserts that the very interesting zeros, the ones that really control the error term in the prime number theorem, all lie on the half line, and just for reasons of later sort of notation and terminology, I'm denoting these zeros a half plus itn. And then the Riemann hypothesis is that these numbers tn are all real. So you can think of them as heights up the critical line. So that's how the prime number theorem sort of came about. But I want to go back to Gauss's letter, because he was really extremely careful in this letter, and I want to highlight a certain particular point. As a good experimentalist, he didn't just give the aggregated data, he told us how he did the experiment. And the experiment involved, as I emphasized earlier, splitting the primes into chiliads. That's not how the data was recorded in the letter. That was an amalgamation of data. He actually had data on finer scales by chiliad. And then he recognized, and he's very careful to say this, that these numbers fluctuate. And on average, that is, if you average over many chiliads, it's only then that you see the logarithmic behavior that we recognize as the prime number theorem. So the question is, that I want to address as the first example I want to give, is what were these fluctuations that Gauss observed? What can one say about the size of the fluctuations and the probability that in a given chiliad you would have a given count of primes? Well, here's some data that I produced recently. This is chiliads starting at 10 to the 9. So in the first chiliad, that is the first 1,000 integers after 10 to the 9, there are 49 primes. In the second, there are 50. In the third, there are 35. These are the fluctuations that Gauss was referring to. And so if you average over all these numbers, you get 47.44. And on the prime number theorem, that is the logarithmic density, you'd expect about 48. So this confirms Gauss's observation of the logarithmic decrease in the density of the primes. But I want to ask about a finer scale question. It doesn't concern what happens if you average over long ranges, that is many chiliads. What are these fluctuations between each chiliad? How can one characterize the fluctuations? This corresponds to something for those who were in the school last week. We're asking here not about primes in long intervals, but primes in short intervals. And we want to know something about the distribution of about the values of these fluctuations. Well, the natural way to characterize this is not analytically, is not really in terms of the primes. It's slightly more natural to characterize this in terms of the von Mangler function, which is log p, function of n. If n is a power of a prime p, it just takes the value log p, and it's 0 otherwise. And the von Mangler function are just gives the coefficients in the Dirichlet series of zeta prime over zeta. And in terms of the von Mangler function, the prime number theorem is just the statement that if you sum the von Mangler function over a very long range, that is all the way up to x, and let x tend to infinity, the sum is asymptotic to x. So there are x terms in the sum, and it's asymptotic to x. So another way of saying this is that the von Mangler function takes on average has value 1. So we're not concerned with long ranges like this. We want to think about summing the von Mangler function over shorter ranges and then asking how, what are the fluctuations from range to range. So this is the subject of a well-known conjecture due originally to Goulston and Montgomery and elaborated by Goulston and Soundarajan. And they do just what I said. So you get the von Mangler function. You sum it over h consecutive integers centered at x. So this is a range of length h centered at x. You sum the von Mangler function over that range. You'd expect, on average, this to be h in size, because the von Mangler function has average size 1. So you subtract off the average, you take the square of the difference, and then you average over the center point of the range. So what we're computing here is the mean square deviation of sums over short intervals from their expected value. And the conjecture, due to Goulston and Montgomery, is that if the length of the range h is anywhere between x to the delta and x to the 1 minus delta for any delta, so basically you want the length of the range to be increasing as x tends to infinity, but not be larger than x, then asymptotically this mean square deviation is asymptotic to h. That's the length of the range, and that's actually the value you'd get if the primes were completely uncorrelated, so if they were Poisson sequence. But there's a correction to Poissonality given by the log of the interval you average over for the center point minus the log of the length of the range. That was the original conjecture of Goulston and Montgomery, and Montgomery and Soundarajan elaborated on that by finding a constant term which one adds on with the claim that then the remainder has a power saving, so it's small. Did I do something? Ah. Okay, good, thank you. So this is the claim, and this is the mean square, and Montgomery and Soundarajan went further and conjectured that the higher moments of this difference converge to those of a normal distribution. So, gamma is Euler's constant. Yes, I should have said that. Thank you. Yeah. So that's the description, if you like, of the variance of the fluctuations that Gauss observed between kiloyads. In his case, h would be 1,000, and x would be somewhere ranging in the first 3 million. Now, one way to approach this, and this is the way that Montgomery and Soundarajan took, is via the Hardy-Littlewood conjecture. So this is a question about fluctuations in values of the von Mangler function, and Hardy and Littlewood gave a conjecture for how the von Mangler function is correlated at different values. They asserted that the sort of autocorrelation of the von Mangler function is given by a certain function of the correlation distance, h, and here's that function. It's an arithmetic function. The details don't matter here for what I'm saying. Simply the fact is that they asserted what the correlations are, and from this formula, one can recover, or motivate, if you like, the Goulston-Montgomery conjecture with the constant term that Montgomery and Soundarajan obtained. And indeed, if you believe a formula like this is true with a sort of optimally good error term, you can prove the Goulston-Montgomery conjecture. So think of it, the Goulston-Montgomery conjecture would follow from Hardy-Littlewood with a very good error term. Now, once you see that sort of correlation or fluctuation, you can look for others. And this, again, is standard in the number theory literature. So rather than looking at different primes in short intervals and looking at fluctuations there, one can instead ask about the fluctuations in the count of primes in different arithmetic progressions. So we can sum the von Mangler function all the way up to x now, but restricted to lie in a given arithmetic progression modulo Q. If Q is fixed and x tends to infinity, this is described by the prime number theorem for arithmetic progressions, which just says that the primes equidistribute amongst the arithmetic progressions which can support them. That is, and the number of those, phi of Q, Euler's function, just counts how many A's are co-prime to Q. Well, in many applications, one doesn't want q to be fixed and x to tend to infinity. One wants to let q to tend to infinity with x. And this is the subject of a conjecture of Hooley, which he announced at the International Congress of Mathematicians in 1974, which does for arithmetic progressions what Goulston and Montgomery did for short intervals. So you get you sum the von Mangler function over n up to x, but n congruent to a mod q. You subtract off the expected value, but now you take the square of the difference again, and you sum over different arithmetic progressions. Sum over a mod q, where a and q are co-prime. And the Hooley conjecture is that that should grow asymptotically like x log q. He wasn't so specific about the range where he expected this to hold, but I think he had in mind, if you read between the lines, that again q lies between x to the delta and x to the 1 minus delta. So this was analyzed by Friedlander and Goulston using the Hardy-Littlewood conjecture. And they showed that even with optimal error term, they could reproduce this conjecture if q lies between x to the half plus epsilon and x. But they weren't able to continue their analysis below x to the half. So it's pretty clear that Hooley had in mind that q could get as small as x to the delta, x to the epsilon, but Friedlander and Goulston were not able to reproduce that using Hardy-Littlewood. And they actually say in their paper they profess themselves somewhat skeptical that it holds below q is x to the 1/2. So the question is this a real barrier? Is there some difference in behavior when q gets below x to the 1/2? Or is this just a limitation of the Hardy-Littlewood method in this context? And I'll return to that later. Sorry? Yes, so q has to grow with x. So q can be as small as x to the delta, but delta can't be 0, any positive delta. So q has to grow with x in this context. If q is fixed, then indeed you just get the prime number theorem, which I put above.
So I guess this is different from that part.
Yeah. So this is q fixed, x tends to infinity. This is q growing with x. Hooley didn't specify exactly how it should grow, but he clearly had in mind it should grow in some way. So we now have these two conjectures. Let me just repeat. There's Goulston and Montgomery, which tells you how, if you count primes in short intervals, how the number will vary as you move the interval around as a function of the size of the interval and roughly where you sit on the number line. And there's the Hooley conjecture concerning primes in arithmetic progressions, the variance of those in different arithmetic progressions as the modulus q grows with x. Now, why am I speaking about this in this meeting, which is related to physics? Well, both these conjectures turn out to be related to Montgomery's conjecture, which we heard about yesterday from a number of speakers. Certainly, Michael and Brian Connery went through this in some detail. So both those conjectures, the Goulston, Montgomery, and the Hooley conjectures, you can relate to Montgomery's conjecture concerning fluctuations in the positions of the Riemann zeros. So if you take the Riemann zeros, which I called a half plus I Tn earlier, so Tn are the heights at the critical line, and you scale the Riemann zeros to have mean density 1, then Montgomery's claim is that there are non-trivial correlations between the heights of these numbers Wn, the scaled Riemann zeros, as embodied in this correlation function. F here is some suitable test function such that the sum converges. And I'll frame his conjecture in a rather unnatural-looking way initially, but for reasons I want to return to later. You can frame his conjecture as follows. He says, OK, you get this correlation function of the zeros, and you compare that to a correlation function for the eigenvalues of some unitary matrix. And what you do is you take an n by n unitary matrix, A, its eigenvalues lie on the unit circle. You look at the phases theta n. You scale those phases to have mean density 1. Call those numbers phi n. And you look at their correlations. You can do that for a given matrix. And now, having done that, you can then average over all unitary matrices, uniformly with respect to Haar measure on the unitary group. And having done that, you can take the limit as matrix size tends to infinity. And the claim is, Montgomery's first claim, if you like, I'm breaking his conjecture into two parts. His first claim is that the zero statistics coincide with this matrix integral. The interesting thing, of course, is that for us is that one can compute this matrix integral. That was done by Freeman Dyson, who showed that this matrix integral is nothing more than the integral of the test function f against a kernel, which we've seen on several occasions already. It's 1 minus sine squared pi x over pi squared x squared. So Montgomery's philosophy is statistics of the zero should coincide with statistics of eigenvalues of a random matrix. That gives rise to a matrix integral. And then the point is that in many cases, this case in particular, you can compute that matrix integral. And this is the answer. So specifically, Goldstone-Montgomery conjecture is equivalent to this conjecture, Montgomery's conjecture. So that's the story on the number field side for counting primes in short intervals arithmetic progressions. We're interested in the fluctuations. One can make conjectures based either on Hardy-Littlewood or Montgomery's conjecture, but we can't prove any of these. There's a sort of circular table of conjectures that one can move between, but we're stuck in that cycle. One can extend this story to other arithmetic functions. So there's nothing special about the von Mangler function in this context. We could ask similar questions about the Mobius function, which detects whether n is square-free, and if so, how many prime divisors it has. The square-free detector function, mu squared, which doesn't count how many prime divisors n has, it just detects whether it's square-free or not. The divisor function, which tells you how many ways there are to write the integer n as a product of two smaller integers, smaller or equal integers, and the generalized divisor function, which determines how many ways there are to write n as a product of k integers. So in each of these cases, one can ask, what are the fluctuations if you analyze sums of these arithmetic functions in short intervals or in arithmetic progressions? And these problems have all been studied in the number theory literature, and the story is pretty similar to what I phrased for the von Mangler function. For all of these functions, there's a variety of conjectures in some cases, sometimes related to Hardy-Littlewood type conjectures. In some cases, for example, the divisor function, we have very little knowledge at all, even conjecturally. And most of the point of this talk will be to analyze arithmetic statistics, for example, the von Mangler function, or of these other arithmetic functions in a unified framework, and see whether we can say a little more about the statistics than has been known previously. And we're going to analyze this in a slightly different situation. This is the function field setting. So we had talks on this yesterday and indeed last week at the summer school. So Alina gave a talk on this yesterday and set out much that is on this slide. So I'll go through this reasonably quickly. The idea is that one has a finite field of Q elements, and we consider the ring of polynomials with coefficients in FQ. And we denote, just a bit of notation, Pn is the set of those polynomials of degree n, and Mn is the subset of those polynomials that are monic. And we'll denote the norm of a polynomial by Q, which is related to the size of the base field, to the power of the degree of that polynomial. It's a standard definition. And the point is that within this world, this is a ring, one can multiply polynomials together and get other polynomials, just as one can multiply integers together and get other integers. And one can factorize in this setting, and there's unique factorization. So one can factorize polynomials uniquely in terms of irreducible polynomials, which can't be factorized further, and those play the role of the primes. So the focus will be on looking at arithmetic functions defined in this function field setting, just as we did earlier in the number field setting, and seeing whether we can say a little more in this context, and whether by doing that we learn more about the number field problems. So we're going to look at statistical characteristics of the fluctuations of arithmetic functions defined over these polynomials, and I have in mind the analog of the von Mangler function, the Mobius function, the divisor function, etc. And we'll be looking at averaging these arithmetic functions over all monic polynomials of degree n, first of all. Then we'll look at averaging over arithmetic progressions, so where we take polynomials f that are congruent to some other polynomial q, a modulo some third polynomial q. That is where the polynomial f minus a is divisible by the polynomial q. And we'll also look at short intervals. That is where we average over polynomials f which are close to some particular polynomial, fixed polynomial a. So we take a polynomial a, and we look at all the f's whose distance from a is bounded by q to the h. Here, I remind you, is what the distance is. So this just means that we're going to look at all polynomials where the first where the coefficients in the polynomial f and a match down to the term which is q to the h. And we'll call this a plus the set of polynomials whose degree is less than or equal to h. And we're going to average over all those. So we have arithmetic progressions, and we have small intervals, just as we do in the number field setting. So the first thing I want to look at is the von Mangler function. In this case, that one defines a von Mangler function of a polynomial to be the degree of f if f is the power of some irreducible polynomial p, and 0 otherwise. This is exactly an analog of the usual von Mangler function, because I remind you the degree of f is a little like the logarithm of f. The size of f is q to the degree of f, so this is like saying that one's setting von Mangler to be log f in this context, and so this really is the analog of the von Mangler function. Well, one wants to analyze statistics of the von Mangler function using a zeta function, and one can define a zeta function as an Euler product, just as one does for the Riemann zeta function. The slight surprise here is that you can compute this zeta function very explicitly. And here I've given you the computation. This zeta function just turns out to have a pole. It's a function of u, where u is 1 over q, and that's it. So this zeta function has no zeros. So this is why one might imagine that this is a somewhat empty subject I'm going to be speaking about. There are no fluctuations in the count of the primes if you average over all monic polynomials m of degree n. So the prime number theorem in this setting, which follows just from the logarithmic derivative of this function here, setting it equal to the logarithmic derivative of this function here, the prime number theorem is that the sum of the von Mangler function over all monic polynomials of degree n is exactly q to the n. And there are q to the n polynomials in this sum, so the average of the von Mangler function is not almost 1, it's exactly 1, and there are no fluctuations around that. So this is a tremendous theorem. It's essentially due to Gauss, although he didn't write it in quite this form. This is a field killer, because what more is there to study if there are no fluctuations? But the point is that if one analyzes slightly more subtle statistics than this, it turns out that one recovers the richness that one sees in the number field. So you can ask, what about Hardy-Littlewood in this context? And this was sorted out surprisingly recently. There's some papers by Bender and Pollack and Lior Barry-Soroka, who's here and will probably speak about these matters. So they established an analog of the Hardy-Littlewood conjecture correlations between values of lambda separated, where f's are separated by k, in the limit as q tends to infinity, the size of the base field tends to infinity. And this is the theorem, which is in its most general form in Barry Soroka's paper, with some appropriate error term. And you see this is a wonderful theorem that one has this. I mean, it's a theorem. We don't have this in the number field setting. But it's a little disappointing because the leading order term shows there are no correlations. The correlations have all gone away. There's no k dependence of the leading order term, as there was an h dependence in the leading order term in the number field. So again, you might think that this world is too empty and void of interesting fluctuations for it to be worth further study. Yes?
Can I ask, if you asked this question above, if you asked it for, instead of empty brackets t, some function field that had, well, a higher genus curve, but there were some zeros,
Yes.
then would you see?
You would see something there, yes. So if you twisted by some characters, you would see something. Yeah. So is this void, or are there interesting things to prove? Well, what I want to convince you is that there are interesting things to prove in this world, and they're the analogues of the questions I raised earlier about fluctuations in short intervals and arithmetic progressions. So something I proved with Zev Rudnick a couple of years ago is that if you sum the von Mangler function over short intervals, so this is, I remind you, is an interval centered at A, which contains q to the h plus 1 terms, not q to the n terms, h is less than n here, and look at the variance of that, and divide by the number of terms in the interval I, q to the h plus 1, there's a limit as q tends to infinity, and it's given by this expression here. It's n. We're looking at polynomials of degree n. It involves h. We're looking at short intervals that contain q to the h plus 1 terms, and there's a constant. And this is the exact analog of the Goulston-Montgomery conjecture, because I remind you, Goulston-Montgomery you can reframe as saying that the variance, if you divide by h, the number of terms in the interval that one sums over here, then you get log x minus log h plus a constant. But the role of log x in this world is just played by n. Log x is the number of terms in the big average here, and the big average here has q to the n terms, and its log is just n. The role of log h is played by little h, because capital H is q to the little h plus 1. And there's a constant which becomes 2. So in this world, you can prove the Goulston-Montgomery conjecture, and I'll tell you how in a minute.
Can you not let Q go infinity?
Sorry?
What happens if you don't let Q go infinity?
Then it becomes as hard as the number field problem. So if you let n tend to infinity with fixed q, this becomes much harder. And indeed, that limit is the limit that a number of people have been interested in here. Giulio Andrade did in his thesis. Andrea Floria has been studying moments in that case. It's much harder, but one can make some progress, but it's harder than the problem I'm discussing here, for the reason I'll get to in a minute. Likewise, in arithmetic progressions, if you sum the von Mangler function over arithmetic progressions, subtract off the expected value, take the mean square, and sum over the arithmetic progressions in which you can get primes, well, more than one prime, you can prove the following theorem, that this variance is asymptotic as q tends to infinity to q to the n times degree of q minus 1. And this is the exact analog of the Hooley conjecture, because q to the n plays the role of x, and degree of q plays the role in the number field of log q. And the slightly interesting feature here is one doesn't see any barrier at the analog of root x, when q is root x. So remember when Goulston and Friedlander analyzed the Hooley conjecture using the Hardy-Littlewood conjecture, they could do it for q greater than x to the half, but not below. Here, there's no similar restriction. So we believe that obstruction that Friedlander and Goldstein identified is just a technical abstraction, and one should be able to go beyond that. Yeah, that's what one do. So we conjecture based on this that the Hooley conjecture is indeed true for Q is between x to the epsilon to x to the 1 minus epsilon, and there is no obstruction at, x to the, at root x. So, yeah, the obstruction is invisible to this method. What is the method? Well, I'll just give you the ideas behind the proofs. If you sum over all monic polynomials, I've explained that there are no fluctuations. So there's nothing to do. But if you restrict yourself to subsets of the monics, then there are fluctuations. Well, how do you do that? Well, you take the sum over all monics and you project down onto either short intervals or arithmetic progressions using characters, Dirichlet characters. This will be pretty obvious that one should be able to do this for arithmetic progressions, because that's exactly how one does arithmetic progressions in the number field case. The slightly interesting feature is that in this world, one can also, with a sieve, project onto small intervals using characters as well. And that one can't do in quite the same way in the number field setting. So here, characters are slightly more powerful than in the number field. So what this does is, when you introduce characters, this twists the L functions, the zeta function, which had no zeros, into L functions which do have zeros, and interesting zeros. And in fact, the zeros of these L functions were proved have been proved by Weil, de Leede, and others to satisfy a Riemann hypothesis. So it has the Riemann hypothesis in this context. The zeros of these L functions lie on a circle in the complex plane, and therefore one can think of them as the eigenvalues of a unitary matrix, which also lie on a circle in the complex plane. And so one can write the L functions exactly as the characteristic polynomial. Each L function is the characteristic polynomial of a unitary matrix. So in this world, the connection between matrices and number theory is a theorem. Now yes, finitely many zeros. In the limit as q tends to infinity, this matrix, it's been proved by Deline, Nick Katz, Chris Hall, and others, these matrices equidistribute in a certain group, depending on the family of L functions that you're averaging over. But that's a theorem that as q tends to infinity, these matrices equidistribute in some group, either the unitary group, the symplectic group, or the orthogonal group. And so the character sums that one has via the projection onto subsets become matrix integrals in the q to infinity limit. And then the point is that the matrix integrals that arise can be evaluated. In fact, in the example I just gave for the von Mangler function, they're very standard matrix integrals, which were evaluated by Freeman Dyson in the 1960s. So one has all the ingredients one needs, and that's how the theorem's approved. But once one does this for von Mangler, one can do this as well for other arithmetic functions. So I'll just give you the example of the Mobius function. So I'm now back in the number field setting, and I'm telling you what's known. The Mobius function, the sum of the Mobius function over a long range, all the way up to x as x tends to infinity, is little o of x. That's equivalent to the prime number theorem. It's believed to be roughly of size root x, a little bit more than root x, and that's equivalent to the Riemann hypothesis. There's a conjecture due to Chowler for the correlations of the values of the Mobius function. This is the analog of the Hardy-Littlewood conjecture. And it basically says, the Chowler conjecture says that the Mobius function is completely uncorrelated. If you look at correlations in any sensible way, in the limit as x tends to infinity. So there are no correlations in the values of Mobius, asymptotically. If you look at Mobius summed over short intervals, this is the subject of a conjecture which goes back to 1968 due to Good and Churchhouse. For those of you who enjoyed on the plane over here the film The Imitation Game, when Alan Turing sacked 2 of the members of his group and hired 2 more, one of them was Jack Good. That's one of the few things in the film that is historically correct. So Good and Churchhouse continued to work for the continuation of Bletchley Park in the UK. It's called GCHQ. Churchhouse was another employee of GCHQ. This paper came out of GCHQ. Goodness knows why, but it's one of the few things that did emerge from this era of work in GCHQ. It's this conjecture, which is that if you sum the Mobius function over short intervals, intervals of length h, then their variance grows with h and has a constant term, which is 1 on zeta of 2. Well, in the function field, one can do the same. There's actually a theorem that the sum of the Mobius function in the function field over all monic polynomials of degree n, if n is greater than or equal to 2, is exactly 0. On the nose. So this is the equivalent of the prime number theorem, which was exact for the stated in terms of the von Mangold function. It's exact for the Mobius function as well. And one can compute the variance using exactly the techniques I mentioned earlier for von Mangold. The Mobius function is generated by 1 on zeta. So you can study its statistics by forming matrix integrals involving 1 on zeta, restricting to subsets of the monics, introduces characters, and that leads you to a matrix integral, in this case over the unitary group, u of n minus h minus 2, involving the trace of the symmetric nth power of u. And this integral you can compute, and it has the value 1. And so in this setting, the variance of the Mobius function is just q to the h plus 1, and that's the precise analog of the Good-Churchhouse conjecture in this context. So one can prove Good-Churchhouse in the function field setting. This range of h actually comes from the range where one can prove equidistribution, so where one has a Nick-Katz type theorem guaranteeing equidistribution. The integral is restricted to n minus h minus matrix of a degree n minus h minus 2, and the power here is n, and that's why the answer is 1. If this power here were less than n minus h minus 2, one would have a different answer. But that's what it is. So this may seem like now it's fun. You can prove the analogs of theorems, of conjectures in the number field setting and establish them as theorems in the function field setting, usually in some wide range of generality, so without the restrictions that have previously been seen, for example, in the Friedlander-Goldstone work. But what I'm interested in now, what I'd like to talk about in the last few minutes, is an application which seems much richer, which we're rather enthusiastic about, and it concerns divisor functions. The reason I want to focus on this example is, in this case, we actually know very little even conjecturally in the number field setting. So let me tell you what we do know. The divisor function dk, the generalized divisor function, is the number of ways of writing n as a product of k integers. The classical divisor function is dn, which you see in books is just in this notation d2. It's the way of writing d as a product of 2 integers. And there's a problem going back to Dirichlet, the Dirichlet divisor problem, which says if you sum d2 all the way up to x, then that's asymptotically given by x times this polynomial of degree 1 in log x. And the Dirichlet divisor problem is to determine what the error term is. That is, if you subtract off the asymptotic from the sum, how big is the difference? For the higher divisor functions, one expects the same behavior. If you sum dk all the way up to x, it's believed that that would be asymptotic to x times a polynomial of degree k minus 1 in log x. And again, one can ask what the size of the difference is. So we're going to be looking at sums of the divisor function in short intervals, intervals of length h, because it's only in this setting, as I'll show you, that one gets interesting statistics on the function field side. So we're going to get the sum over all the way up to x plus h, subtract off the sum up to x, and look at that difference, which is delta k of x and h. So it depends on where you sum between x, starting at x, where you start at x, and how far you go, capital H. And one can ask about the variance in this case, and there's a great deal of work being done on the number field side on this problem. So there's a theorem. I'm amalgamating theorems of several people here, Utila, Koppler and Salerno and Ivich, which says that if h, that is the size of the short interval, is between x to the epsilon and x to the half minus epsilon, then the variance of the error term in the divisor function sum is asymptotic to h, the size of the interval, times a polynomial of degree 3 in the variable log x minus 2 log h. That's their theorem. They don't write down this polynomial. They simply prove it exists and that it has a positive leading coefficient. Presumably, they thought the polynomial is not sufficiently interesting to actually go to the effort of calculating it. That is some effort, of course. For the higher divisor functions, dk, we know much less. So I want to emphasize this theorem holds in a slightly restricted range. It's h going between essentially x to the epsilon and x to the half minus epsilon. So it covers half the range. You could ask what happens for h greater than x to the half, and that's not covered by this theorem. If you take k greater than 2, the generalized divisor function, very little is known, although there's some work that's concurrent with ours, very nice work of Steve Lester, who's shown in parallel to work I'm going to describe here, that for k greater than or equal to 3, and if you're assuming the Lindelof hypothesis, you do have a formula for the variance of delta k. It's given by something which you don't need to pass. There's some sort of details that won't concern us here. The main thing is that this depends, it's proportional to the size of the interval, h, which in these units is just this term here, times log x to the k squared minus 1. And the details are given here, but you don't need to remember those. For the cognoscenti in the audience, this factor ak is just the arithmetic factor that appears in the moments that Brian Connery spoke about yesterday. Now, he can prove this over a rather restricted range. It happens to be exactly the range that, or the extension of the range to general k of the sort of Utila-Ivich type theorem. So one has these results only in a small window. And one wonders what happens outside that window. Is this a technical restriction, a technical limitation of the method? Or is there a deeper reason why one can only prove things in a limited window in the number field setting? So please bear that question in mind. These theorems are restricted range. So was Friedlander and Goldstone. The Friedlander-Goldstone restriction on the function field side doesn't appear. That's a technical limitation in our view on the number field side. In this case, one has a similar restricted range one can prove things over. Is this a technical limitation in the same way? So bear that in mind. And I should say Lester's results for k equals 3 are unconditional in an even more restricted range. Beautiful work. So the question is, if you get the generalized divisor function and look at its variance over short intervals, is this always a polynomial in some appropriate variable? Well, let's look at the function field case. If you sum the divisor function over a short interval and then average over the center point, so basically you're summing dk over all monics of degree n, in this case you can prove an exact formula. And it's just q to the h plus 1, which is what you'd expect, times a binomial coefficient. And this binomial coefficient is, of course, just a polynomial of degree k minus 1 in the variable n, which is the analog of log x. So this is the analog of the sort of general expectation that on average you'll get a polynomial of degree k minus 1. This is just the thing I started with on the divisor problem. What we want to do now is not average over all the monics, but to restrict ourselves to some short interval and then take the variance. And the first theorem I want to explain, which is due to, it's a sequence of theorems, so this may not be transparent to start with, it'll become transparent as we go on. It's due to myself, Brad Rogers, Edvar Rodity Gershon, and Zeev Rednik. And the idea is that you sum the error term in the divisor function, a divisor sum. You look at the variance of that over short intervals, and then compute that variance. And the answer is it's asymptotic to h. This is as q tends to infinity, times some function, and I'm going to tell you what this function is in a minute, of n and h. So this uses the machinery I set out earlier of equidistribution. This is as far as equidistribution gets you. The question is, what's this function I? Well, it's a matrix integral. And it's a matrix integral that I'm not aware has appeared before. So we start to get into new territory in random matrix theory. So if you ask this question, the matrix integrals that appeared earlier were all known. This one, it seems, hasn't been studied. It looks a bit unnatural from the matrix side, but on the number theory side, it's very natural. So the idea is that if lambda j is the exterior jth power representation of u, you're just computing sums of traces of exterior powers, the modulus of that squared, integrated over the unitary group. So it's a matrix integral. Turns out this matrix integral well, by definition, actually, it's 0 if m, this argument here, is bigger than k, the index times n. So we only have to restrict ourselves to where m is less than kn. It's non-zero in that range. You can prove that. You can prove this integral satisfies a functional equation. It's symmetric around m is kn over 2. So it's like a function equation satisfied by the Riemann zeta function. It's a reflection symmetry around the halfway line. So we actually only need to take m up to kn over 2. If you take m up to n, so that's the first step in where we have to evaluate it, you can evaluate the integral in closed form, and it's just a binomial coefficient. So it is a polynomial of degree k squared minus 1 in the variable m. So in particular, if we set k equal to 2, you get a cubic polynomial in the variable n minus 2h. This is the exact analog of the Utila-Ivich result. They established the existence of a polynomial, but didn't calculate the polynomial. The interesting fact is this polynomial, if you do calculate it, is quite simple. It's a binomial coefficient. And I don't believe this kind of structure had been anticipated before in these problems, that the polynomials that appear are not sort of randomish polynomials. They're actually just binomial coefficients. And this is true in general. And in fact, this range corresponds precisely for general K to the range of Leicester's results. So the question is, outside this range, is the answer also a binomial coefficient? And the answer is no, it's more subtle. So this integral I can be evaluated exactly, not asymptotically exactly, as a count of lattice points. See, time is moving on, and so I'm not going to go through in detail. This matrix integral I is exactly equal to a sum of lattice points in some particular, restricted in some way. So it's lattice points restricted by certain inequalities. And those who are cognoscenti will recognize the sort of Gelfand-Zetlin pattern that often arises in representation theory, and some other restrictions on the lattice points. Once you've written I as a sum of lattice points, it's easy to compute the asymptotics then. You know how to compute count lattice points in some volume. To leading order, it's just the volume you're counting over. So you can compute the asymptotics of the integral I, and the surprise is, first of all, you can write that in closed form as some simple integral over a simplex. The second surprise is that this formula one gets is an asymptotic formula of matrix I to the power k squared minus 1, n to the power k squared minus 1, but the coefficient is not a polynomial. It's a piecewise polynomial. So it's a different polynomial